So for our next talk, we'll have challenges and opportunities of performing path planning for healthcare robotic systems with the Julia language. So let's welcome our speaker.
Thanks. Good. So it won't be too techy, but let's try to get it. That's me. Just a note that I'm working at Siemens Healthineers. So it's a healthcare branch of Siemens where we do all this imagery, machine, and also advanced therapies. I have some background rather in aerospace industry and modeling and simulation. This is the co-author. I wanted to make a slide with everything, but when he told me that basically he won four times the world champion at RoboCup, I thought that was enough as a slide. So I won't put more. And we are doing quite some robotic there, so it makes sense to have him on the team. I'm going to introduce the problem we are going to solve, how we have solved it so far, and it's two approaches, one static and one dynamic. And then I'm going to say, okay, why we are trying to solve it differently and go with some results, and mostly perspectives. Conclusion is one sentence. So the problem we want to solve is this staff shortage in the hospitals. We have really problems where all the physicians and nurses, they have a lot of workload, and we basically want to make things simpler for them. And if you look at this machine, it's able to do like 3D scan with X-ray. So you have some kind of like dancing between these two parts, which emit the X-ray on one side and receive it on the receptor on the other side. And if you want to automate all that, then you can save a lot of work. You can say, I want to target this part of the body for my imaging. So basically you want to say, go there, and the machine goes there. But also we're looking into helping the assistants in the lab with some robotic systems. And that's a research project that we've done with all the names that are there. And the robot that is actually here on the left is Aurora, and is actually like a robotic arm that can bring you like some materials on the scene. Good. And there are some problems. As soon as you want to make things autonomous, you want to make sure that you go from point A to point B without colliding with people or machines. And that's what we are going to talk about today. So the first thing we did is to do something really, I don't want to say basic, but like it's really static in the sense that we discretized, well, we basically imported a map of the floor, of the room. We discretized it, like meshed it. And then we did like some A-star path planning algorithm, which is static. And as you can see, for example, here you have a system which is like this rectangle. Let's say it's a bed going to an MRI system. Then you see that at the end, the behavior is basically not necessarily physical. Like the rotation at the end is actually not something that the bed can easily do, and it's like super heavy bed, and you can have super heavy patient on top of it, so it's really hard to maneuver. On the other side, it's super fast. Like you just compute the thing in 20 milliseconds, 50 milliseconds. For a really long pass, it's like 100 milliseconds. It's still like super fast. But we wanted to be a bit more physical. So what we did in the first place is we did a Modelica model. And based on this Modelica model, we wrote an optimization with the Optimica language on top of it. And we used dynamic optimization using Casady to basically optimize for the path without colliding with the objects. It's physical, like all the motion is basically constrained by the physical behavior of the system. So that's something we can do. And it's really not fast. So that's the drawback here. So we get things, but we cannot like put it on the product, like on the hardware itself, and using it for the path planning, right? Like it's upfront. So you can get it why we want to try new ways, why we want to actually to do something that would be fast and that would be physical. And well, as you see, we had like two parts. One part which was really algorithm based, and the other part which was more physical. And we basically believe that with Julia we can have all that. So at the moment, I'm using modeling toolkit and Julia code. And well, I believe that with that we can also like get even simpler with the DSL that it provides, and then we can actually do the model physically with the diode language. And the goal is to be fast and physical, right? So the first implementation we did is basically adding a fun stuff on top of what we have done so far. So we take the map, we basically compute a cost based on the map, which is a function of like the distance to the wall and so it's 2D for the distance, and the third dimension is basically the angle of the system you have. So if it's a square, it's kind of easy, but if it's a rectangle, then you have like for some angle you have to have more margin basically to before colliding to the wall. So that's part of the compute cost. So we have a 4D at the end cost map because you have the cost as a fourth dimension. We compute the image is just the same, just in different perspective. We compute the path with an A-star algorithm so that we get a first initial trajectory for our dynamic optimization. And this dynamic optimization runs at the moment with modeling toolkit.gl and dyad control systems.gl for the optimization path. I have the name of the function from dyad if you're interested, but I forgot about it. In first result, where it's really, really fast, like compared to what we had in Modelica plus Optimica at the moment, I think we have a factor. In the abstract, I write 5, but from what we got in the latest, it was even faster. Like we got like below the second for the compute, and I think there is lots of things we can still optimize there. It's a great feeling because you code basically the algorithm, all the pre-processing, everything, and the physics in the same language. That's really something that basically avoid you to have like this barrier between the two languages. There are some minor drawbacks, which is more like on the change of culture. Like usually we had this two language problem, but now we have like this two engineers problem. Like it's not necessarily like the same person that codes the algorithm and the model. And what we are doing is like, okay, now you can do all. Yeah, but I don't know both of them. Like, but yes, it's okay. We can transition to that. And the result of that is I still have some bugs in my code that I need to solve. So there are some like successful optimization that basically hit the wall, but I will solve that. It's just like a question of time and prioritization. What we lack the most at the moment, but I've seen in the recent webinar that it's going to be really possible soon, is to have a streamlined way to put that on the hardware. Today, if we do that in C++ or Python, then we can just use ROS and push it to the hardware. I want that in Julia. I see it's coming. I'm super happy. Oh, I thought I would run out of time, but I'm actually good. So the conclusion is straightforward, but in terms of perspective, I put it small because I'm not so proud of it, but I have to solve my bugs. And all the animations you've seen are not in Julia, so I need to update that. But basically, I want to try transitioning to the dyad language for the model itself. I also think that the analysis on top of the part of the dyad language will bring a lot to the workflow. So that's something I really want to investigate and try that out, trying to get a license for it. I want to test, maybe I wrote it wrong, but I think for now it's the Julia C part for hill testing. Let's see if that's the best way to do it, but I'll talk with Ranjan. Then I want to expand to 3D plus planning. Everything you've seen here is 2D. As soon as you want to make like what the multi-term racks is, this machine here which is dancing in 3D, then you want that in 3D, like the path planning. You want to be able to make the 3D scan on the table, but you also have a bulking wall stand, I think it's called. Like it's a wall basically that the patient can be standing so that the organs are like basically falling down naturally, and you want to basically make some imaging when the person is standing, and you want to move smoothly from one to the other, avoiding the table, avoiding the bulking wall stand. So basically, that's something I want to expand on. Last but not least, my colleague Marco is working on this semantic world where we basically want to add some notion of what are the objects in the room and try to add more basically discrimination around path that goes near, for example, patient or product like that could be dependent on the life of the patient, like the what it's called, like the breathing machine, for example. You don't want to hit that, but if you hit something like the door, it's less a problem basically. So we basically want to go the green way and not the yellow way on this one. So that's something we want to implement. He has done that in C++. I want to have that in the path planning also here on Julia. Good, that's all.
Thank you so much. We have time for questions.
First of all, awesome presentation. I'm curious. You mentioned that you kind of use a static environment and then do an optimization. Have you looked into things like SLAM or whatnot, like simultaneous localization and mapping for dynamic environments as well, and incorporating it into this loop?
Yes, but not in Julia.
Oh, okay, interesting. Yeah.
We have done that, yeah. And actually the code is entirely running on the Aurora robot that you see.
I see.
And it's always like getting all the information from the radar, from the lidar, and just adapting and in the loop, always updating. Yeah.
Very cool. Oh, did you? I'm curious. Was there an attempt to try and do it in Julia, or is it just because it works as is and there's no need to?
Yeah, it's not yet there. It's like that's as much time as could dedicate it to the topic,
Understood.
but I will progress toward that. Yeah.
Very cool. Yeah.
We have time for one more question.
Sorry, I should have let somebody closer ask a question. So in the initial simulation you had it following some trajectory, avoiding some obstacles. Presumably those are all completely static and it knew about those a priori, right? And then in your, yeah, so like that one, you just, or just go to the next one, the animation. I'm just thinking about the,
This one is dynamic,
blue,
yeah?
the blue things there. It's somehow been informed about all those blue lines in advance. In almost the last slide, you showed some other potential obstacles. I'm just curious. Maybe you addressed this point. I'm not sure. Is the idea that it would be dynamically constructing a view of the obstacles in the same way that, for example, self-driving cars are doing that, and then maneuvering around them?
Yeah.
Yeah. Okay.
Yeah.
All right.
So once it runs on the so yes. So in it basically we have both scenarios. So and I would like to push for always like the simplest solution. So here it's basically an MRI room and it's like really, really clean. Everything is really, we know where everything is. Let's start with a map. Nothing will move. We'll have a sensor just to make sure that if nothing has changed, but we won't adapt the path unless there is a change. But for for example, the CAST lab or whatever, like I was showing with this Aurora program, then here we have like dynamic adaptation based on how the people move and how all the equipment is moved around. It's a nightmare here because like you want to have like this this type of mobile imagery C-arm that comes to make imaging when you do the operation, and they go out to basically give you more room to operate and then bring back to get another image. And the robot has to be aware of that and always seeing where these equipments are. And there are like cables on the floor, and you want to avoid that because you don't want to.
Yeah, and I suppose there's also the scenario where the robot's in the way of somebody, and it can't detect that it's in the way, right?
Yeah.
Somehow the person has to gesture or something to tell it to scoot over or something. Yeah.
Thanks. Yeah.
So let's thank our speaker again.
Thank you.